Good morning, Allie.
Morning, guys.
Morning.
Wake up, Allie.
I'll have you know, I've been awake since 7.
Okay.
Rick, you've also been awake since 7, right?
I've been awake since 5 minutes ago.
Do the Brady Bunch thing. Who are we missing? All right,
Nick.
Good morning, everybody. You ready to do this? I am. A few things to, just before we get started. I think I'm going to change around my office hours a little bit. I'll keep what I've got, but I want to add some more to add an hour on Monday and add some more on Tuesdays and Thursdays. So once I figure out that schedule, I'll let you know. Let me also go ahead and start sharing. Okay. All right. What we're going to do today is, as far as I'm concerned, we finished off complex analysis. Woo! I know you're thrilled about that. And we're going to start with Fourier series. So this is hopefully some familiar territory. The overview for today then is just a reminder of what Fourier series are. Oh, there goes my dog. The mail's here. You asshole. All right. So what they are, when do we use it, especially in terms of solving physically interesting ordinary differential equations, partial differential equations, electronics, things like that. We're going to combine what we've learned from complex analysis and look at complex Fourier series. I'll move this screen so I can see it. And then we're just going to do a bunch of examples heading towards Fourier transforms ultimately, but also discrete Fourier transforms. What do you do with data? With respect to the next homework, so just to give you a heads up on where we're going, you had the last homework was due yesterday. I'm still collecting it if you haven't finished it and trying to be a little more lenient with the deadlines. Just let me know if you need help or extra time. For problem set 3, what I've done is, since we skipped over the integrals, I've added, so I want you to not do problem 12.84, which is was another set of integrals, but instead I want you to do 11.89, which is in the integration section. In fact, it's showing exactly this, that the integration of sine squared x over x squared dx is equal to pi. Your book has it equal to pi halves, so your book's wrong, at least as far as I can tell. This is a well-known interval. Well, I don't know if it's well-known, but it's known, and it's not equal to pi halves. I think what they did was when they split it as an even function, they did something with a factor of 2. Anyway, this is one way of calculating pi. So that's the answer you should get. Any questions? All right. So Fourier series. Hooray! So we'll start with our usual introduction and definition. And I've already kind of spoiled it with what the overview is. It's an expansion of a function, right? In this case, it's an expansion of a periodic function that technically can be complex. That is, it can be real, could have imaginary parts. We'll start with just the real functions. And it's periodic on an interval, at least the way we're going to start right now, minus pi to pi. We can also look at that interval as well. It changes things just slightly. And given that, we know that we can write f of x as a linear combination of sines and cosines, right? With essentially different frequencies. And that's where this becomes really important, is that we can see ultimately when we look at the Fourier transform. And I had a couple of questions, or I had at least one question about the utility, or what do we mean by Fourier transform as opposed to Fourier series. In a sense, in essence, we're kind of going back and forth. So Fourier series, we're taking a function and we're trying to represent it as a bunch of other sines and cosines. When we do Fourier transforms, that basically transforms from real space to frequency space, and it allows us to pick out those important frequencies. That's why we do Fourier transforms when we do spectrum analysis, right? When we want to pick out power series analysis. So as you probably are familiar, we can break this up into cosine series and a sine series. That is, a naught some constant is equal to n equals 0. The sum of n equals 0 to infinity of a sub n times cosine of nx, plus the sum from n equals 1 to infinity of b sub n sine of nx. This is equation 3.8.1, since we're starting a new section. And of course, where the rubber meets the road is trying to find those a sub n's, right? So you remember what the a sub n and b sub n is? What's a sub n? Even if you don't know it off the top of your head, what does it involve?
You do some weird integral tricks or something. You add a sign to both sides.
Well, okay, so for a sub n, we know that it has to deal with cosines, right? So it's kind of a weighted integration, right? So 1 over pi from minus pi to pi, since that's the period we're on, of this particular function f of x times cosine of nx dx, right? And the reason why that's there is that we're going to be stepping through all of those different, essentially those different periods or those different frequencies. And then b sub n is equal to 1 over pi minus pi, the interval from minus pi to pi, again, of that f of x sine of nx dx. Okay, so most of what our job is when we do these Fourier expansions is to solve for a sub n if we know f of x. So it's maybe one of the most straightforward, well, the most straightforward example would be a single sine curve, right? And we'll see that with orthogonality, everything drops away, right? You wouldn't expect a terms if the function was just sine of x, right? So if we look at an example square wave, then we have something that, let's see, let's use green. Looks like this, right? Where let's say that this is 0, and this is a height h. This is minus pi, and this is pi, and this axis in this case would represent time. In other words, it's this square pulse. And one of the reasons why it's interesting is because it's discontinuous. One of the reasons why, and I'm sure you're aware of this, that we use Fourier series and why they're so important is so we can take a discontinuous function and represent it as a continuous function, right? And if it's a continuous function, then we can do derivatives on it, we can integrate it, we can do all sorts of great stuff with it, right? So the way to represent this then is f of x is equal to 0 from, say, minus pi to 0, and h from, that's a 0 to pi. Okay, so first step is usually to find a sub 0. Remember the a series, cosine series, but because of the nature of the cosine series, we set apart a sub 0. So we have a sub 0 is equal to 1 over pi from the integral times the integral minus pi to 0 of 0 dt plus integral from 0 to pi of h dt. This is all in parentheses, and it's pretty easy to see that that's just equal to h. So our first term is equal to h, right? Then we do the a sub n's, that's 1 over pi, 0 to pi, times h cosine of nt. So we're just skipping over the 0 part, right? And this is a pretty straightforward interval, right? This is 1 over n pi sine of nt evaluated from 0 to pi, and that's equal to 0, 1, 2, pi, infinity. 0, yes, 0, right? Sine of 0 and sine of n pi, right? Morning. B sub n is then equal to 1 over pi times this usual integral from 0 to pi of h of sine of nt, and that's equal to minus h now over n pi times cosine of nt evaluated from 0 to pi. And that's equal to minus h over n pi times cosine of n pi minus 1, right? Or h over n pi times 1 minus cosine of n pi. And you've undoubtedly saw this in maybe E&M or something like that, where clearly this is going to flip signs. So basically, this will be equal to 2h over n pi for n odd and 0 for n even. So what does this mean? What have we done? Remember, the a sub n's and the b sub n's are what we're after. But we need to put that back into equation 8.1. And so we have our f of x is equal to h over 2 plus 2h over pi times sine of t plus 1/3 sine of 3t plus 1/3 sine of 5t. Okay. This is a great demonstration of Gibbs phenomena, right? If we were to just cut all of this off, right? Remember, even though it looks a little backwards, we solved for the b sub n's ended up being cosine terms, but the b sub n's are coefficients in front of the sine series. And if you think about our function, right, the function we're trying to fit looks like that. And our first term is that. Our second term is something like that. Our next term is something like that. And so when you add this all together, you end up with something that kind of looks like that, right? You have that little overshoot, which is the Gibbs phenom. Okay. Probably something that you've seen before. If you haven't, great. Now you have. But I'm sure that when you did E&M, this is the first, at least you saw that in E&M when you looked at Laplace's equations. How are we doing? Good? Okay. So what might be one problem with what we're doing here, or one thing that we have to make sure happens with what we're doing here? Let me put it another way. We are representing a function as what?
A
What do we,
sum of two continuous functions.
as a what of continuous functions? Can you say that
The
again?
sum of the two continuous functions.
Okay, it's a sum of continuous functions, but in particular, if we go back up here, right? What are we doing with this function f of x, which may itself be continuous, right? We've only looked at this discontinuous function, but what are we doing explicitly that sort of was the reason why we started this class the way we started this class? Hint.
To integrate it.
Well, what are we doing over here?
Are we worried about if those sums diverge?
Yes. So we are representing a function f of x as a series, right? Possibly two series. And so one of the things that kind of gets glossed over is do our Fourier series converge, right? And one way around that in terms of, I mean, we could and we should take everything that we do from a Fourier series and check its convergence. Use some kind of, I say the Weierstrass test to determine that the power series that or the series that we are constructing converges on the interval of interest. Often that's a little bit arduous, so we can use instead the Dirichlet theorem. So the Dirichlet theorem has, I mean, usually when you hear about Dirichlet, we're referring to boundary conditions, and that's no different really from here. The idea is if you have f of x, so if f of x is periodic with, say, a period p equals 2 pi, and f of x is single valued. So we're going to be basically making sure that f of x is not pathological in any way. Right? A single valued between minus pi and pi, and has a finite number of discontinuities. So the only thing that is potentially dangerous with the function is that it can be discontinuous. In fact, that's where Fourier series really kind of earns its supper. And has a finite number of maxima and minima, which frankly is hard to not have, but and finally, the integral from minus pi to pi of the absolute value of f of x dx is finite. Then, okay, so let's just take a second here. This is the statement of the Dirichlet theorem. We are going to only focus in most of this class and most of your career on functions that meet all of these criteria. They're periodic, they have a finite number of discontinuities, they're not some bizarre function that drives to infinity, and the integral exists, at least the absolute value of the integral exists. If all of that is true, then the series expression in 8.1 converges. And not only does it converges, but it converges to f of x at all points where f of x is continuous. That's number one. What about discontinuities?
Is that like the Gibbs phenomenon that you mentioned?
Not quite, because the Gibbs phenomenon is kind of an overshooting of a sharp discontinuity. So we're looking at where it, and the Gibbs phenomenon actually happens right before the discontinuity. So right at the discontinuity, where does essentially the Fourier series converge to?
Also f of x.
Well, right, the average value, right? So so at the jumps, put a comma here, and at the jumps in continuity, the Fourier series converges to the midpoint of the jump. In other words, if we have something that kind of, if I can do this any justice, and you notice that we have all of these discontinuities. If it's periodic on our interval, then we know that our Fourier series is going to converge at these midpoints. Okay. Why is all of this word salad important? It's pretty huge, actually, right? And I'm kind of stating it without proving it, but what this means is that if the conditions of the Dirichlet theorem hold, you have convergence. Just kind of repeating what the theorem says. That means you do not need to test for the convergence of the series you find. It's also kind of a uniqueness theorem, right? Whatever series you find using the Fourier series on something like this means that's the Fourier series. It converges uniformly to f of x. Okay? Now, like I said, that's a bit of word salad, but that's kind of been, and maybe that wasn't up front when you were taking this as an application of, say, E&M, or solving other partial differential equations. But this is behind why Fourier series is as powerful as it is. It's a convergent series, infinite series, and it's convergent because it matches all of these conditions. If one of those conditions fail, it doesn't necessarily mean it's convergent, but we have to make sure, we have to then do the convergence test. Okay. And if you dig around up here, you might find versions of our conditions for convergence from the first week in class, like something like that, right? So we're kind of taking all those pieces from the first week. All right. I need a coffee because I've been talking a lot. Any questions? And I have to admit that your textbook is not very clear about this at all. We're kind of I'm expanding that first section in your textbook. But I want to make sure that we're all on the same page here. Please let me know if you're still writing. Good. All right. A couple of other things that we've run into, I'm sure. Completeness and orthogonality. So one, completeness. What do we mean when we say something's complete like this? It's kind of buried in 8.1, but it's just bringing it out explicitly. When we say something is complete, what do we mean by that mathematically?
It's fully defined on the interval.
Yeah, I mean, that's good. What is the other piece to that? For example, you probably ran into completeness in quantum, right? You started with, I think everybody here is now taking quantum using the textbook where you focus on the Stern-Gerlach experiment, right? So in order for that view of quantum to proceed, you explicitly rely on completeness. And what is the foundation of understanding quantum from the Stern-Gerlach experiment? Okay, time out. What's the Stern-Gerlach experiment?
Spin up or spin down.
Okay, not only spin up or spin down, but what would we say about those two states?
Z or X or Y.
Well, but
Different
we have
order.
spin up, we have spin down, and in fact, it's not that they're spin up or spin down. What are they?
They're orthogonal.
They're orthogonal, that's the other piece of this, but what else? If we want to fully describe something quantum mechanically,
It's a probability amplitude of being spin up or spin down.
right? Which means that we are, starts with an L and rhymes with linear combination, right? So we're, the idea of completeness is that we have a function f of y that can be represented by a function c, infinite sum of cn times f sub n of y through linear combination across that space that spans that space of interest, right? Maybe that was just a little too on the nose from the first part. I think you guys all knew that, but the other part to this is just what was mentioned too, is orthogonality. Right, so Fourier series are complete, right? So that means that they can represent a function as a sum with these coefficients. And the orthogonality means that, for example, we can look at the integral of f sub n of y prime and f sub n prime of y dy, and that equals 0 for what condition? It's an n prime. Actually, let me rewrite this, sorry. N prime, there we go. What's the condition for orthogonality?
When n does not equal n prime.
Right, so that, right? So for example, the integral from 0 to a of sine n pi y over a, which is probably something that you saw in E&M, not to beat that dead horse, times sine of n prime pi y over a dy, that equals 0 for n prime not equal to n, and a halves, I think, for n prime equals n. We can also, I guess say 4. We can also expand this, haha, sorry. Oh, it's early in the morning for me too. Well, not really. Well, yeah. For the complex case, so for complex functions, we might look at the integral from 0 to 2 pi of e to the imx and e to the inx dx, which is equal to, in this case, 2 pi times the delta function n sub n, which we'll come back to later. Okay. We can write this in a number of different ways, right? And in particular, if you look at other cases on, say, the interval 0 to 2 pi, we might have 0 to 2 pi of sine of mx sine of nx dx is equal to pi times mn and 0 in those two cases. 8.6. You do the same thing for cosines and sine and cosines. In fact, you do the same thing for cosine. One of the things that comes out of orthogonality then is the integral from 0 to pi of sine mx times cosine of nx dx. That's equal to 0. What's the condition for that to be equal to 0? This is a little trickier.
When they're not equal?
Actually, yes. Actually, for that, in this case, all n and m, right, when you've written it like that. This is going to allow us to get rid of some Fourier terms. Okay, on the interval 0 to 2 pi. So the nature, the even and odd nature of these functions on that interval. Okay. All right. As I mentioned, we can do this for complex functions and a complex series as well, which leads us to Fourier transforms. So this is an intro, more like an aside on the complex form for Fourier series. So for the definition, we'll recall our complex way of writing sine of nx. So what is sine of nx equal to? You all know this.
E to the I n x minus e to the I n x over 2I.
Over 2i, exactly, right? And similarly, cosine of nx is equal to e to the I nx plus e to the minus I nx, but this time over 2, right? So we can write, let's see, I'm kind of editing my notes as I go. F of x, this is where the power of complex analysis from the last week and power series from the first week come together. We could write f of x as c naught plus c1 e to the ix plus c minus 1 e to the minus ix plus c2 e to the 2ix plus c minus 2 e to the minus 2ix, and so on until we get to basically n, the sum of n from minus infinity to infinity of this coefficient times e to the I n x. We've just taken our cosine and sine series, rewritten them as exponentials, right? So this is b1. All that's left then is for us to find out what that Cn is. Right, so this is our Fourier series for, I guess I should write this as equals to, for our complex representation for a Fourier series. So it means that, again, we need to identify what the coefficient is. So maybe without the actual expression, what do we have to find? How do we go about finding these C sub n's? And again, this is for a periodic function on minus pi to pi. What did we do to get the a sub n's and the b sub n's? What's the essential idea rather than necessarily the actual integral?
Integrate the function times e to the I nx.
Yeah, close. But that's the idea, is right. It's going to be this weighted 1 over 2 pi integral from minus pi to pi f of x e to the minus I n x dx. And that takes care of us going from minus infinity to positive infinity. Another way of writing this is that we can write Cn is equal to 1/2 times an minus I bn, and C minus n is equal to 1/2 an plus I bn from our previous, put this B4 and B5, B3 and B4, from our previous definitions. Okay. So that works. Whatever f of x is, this is just using a complex, just using the complex form of sine and cosine. And the way to test if this makes sense is to go back to our original example. So again, let's go back to that same square wave. So Cn is equal to 1/2 pi times the integral from -0 or minus pi to 0 of e to the minus I n x times 0 times dt. Remember, this is just the square wave. Plus 1/2 pi times the integral from 0 to pi of e to the minus I n x times h dt. So this is equal to h/2 pi times e to the minus I n x divided by minus I n, just doing that integral, evaluated from 0 to pi. Right, and that should get us h over minus 2 pi I n times e to the minus I n pi minus 1. If I did all of that math right, I think so. Right, so we know that we can represent this in terms of cosines and sines of n pi, right? And so then this is equal to h over I pi n odd and 0 for even. Okay. And we can compute C0. That's just 1/2 pi, 0 to pi of h dt as before, and that gives us h/2. Okay. So the coefficients are different, right? The whole purpose of this is that the coefficients are complex, right? So even though that's an I here, that's an I here, that looks like it's strangely different from what we got last time, we then have to put it back into our power series. So f of t now is equal to the sum from minus infinity to infinity of Cn e to the I n x. And so that's equal to h/2 plus h/I pi times e to the it plus 1/3 e to the 3it plus 5 e to the 5it, and so on, plus h over I pi, and now the minus, the negative part of the series, minus e to the minus it minus 1/3 e to the minus 3it minus 5 e to the minus 5it, and so on. And you can start to see that we're defining terms of a sine. So this ends up being h/2 plus 2h over pi times e to the it minus e to the minus it over 2I plus 1/3 e to the 3it minus e to the minus 3it over 2I. In other words, we get h over 2 plus 2 over h pi times sine of t plus 1/3 sine of 3t, and so on. So either representation gets us the same result, which should be comforting. That's a lot of writing, so take a minute to shake out your hands, get some water, some coffee, ask questions if you have it, or finish writing.
Is there any reason why we would want to use the first form other than the complex form if we knew that the function was completely real?
Generally not. No, I mean, if you could make if I think the only where it becomes really important is when you want to beat something into strictly a power series instead of a set of sines and cosines. The sine and cosine representation of that is really useful when you can identify that it's purely a sine collection of sines and purely a collection of cosines. I think if you look at what we just did here compared to what we did up there, the previous example were fewer steps and a little bit more obvious than this example. If, on the other hand, it's a combination of sines and cosines, this might be a better way to go. Yeah. The other thing that's nice about the sine and cosine expansion is that if it's one frequency, it'll pick that up right away. I mean, this will too, right? In fact, what this is leading us to is Fourier transforms. I mean, this is sort of a truncated Fourier transform, if you think about it. Fourier transform would be an infinite interval of e to the I omega t times that function of t, right? Have you guys, I forget if I've asked this, have you seen Fourier transforms explicitly that you're aware of, maybe?
Maybe in Alan Parks's class.
Okay, all right. How about in physics?
I think we did do a little bit in electronics, or not electronics, E&M.
E&M, okay, sure. Oh, awesome. There are like 4 pelicans in my yard. Sorry. Aw. That's great. Okay. We ready? Not here. All right. Let's continue on with complex variables. So in the previous case, make sure I'm doing the right thing here. Yeah, we tried to represent everything in terms of real, both the series and the function. What we want to do is consider, and this is sort of set up in the last section, consider a convergent complex power series. So again, we have f of z is equal to the sum from n equals 0 to infinity of c n z to the n, which we can also write out as the sum of n equals 0 to infinity of cn r to the n e to the I n theta, as we've, let's see, I want to make, sorry. Oh, there we go. As we've done before. Okay. Let's let u of r theta be equal to the sum from n equals 0 to infinity of cn r to the n cosine of n theta, and v of r theta be equal to the sum of n equals 1 to the to infinity of cn r to the n sine of n theta. this brings us to something called Abel's theorem. And that is if u of 1 theta, that is for a unit circle, unit in the complex plane, and v of 1 theta are convergent. So we've constructed a set of power series that we're going to map to this f of z for all theta. So they're uniformly convergent, right? Both u and v are uniformly convergent. Then u of 1 theta plus I of v 1 theta is equal to the limit as r goes to 1 of the function r e to the I theta. Okay, so we have time to look at this. So why would we want to use this? Well, we might want to use this, and this kind of gets back to Stephen's point of a question of why would we use this form or cosine and sine form. So let's consider the sum n equals 1 to infinity of cosine of nx over n on the interval 0 to 2 pi. This series converges across the interval. It's absolutely, so what we can write is the sum from n equals 1 to infinity of cosine of nx over n is equal to the limit as r goes to 1 of the sum r to the n cosine of nx over n. This is absolutely convergent for r less than 1, or the absolute value of r less than 1. Not clear yet why this is a great savings, but what we can try to do is try to form a power series. Remember, our goal here is to take something and create from it a power series expansion, essentially. Basically going right back to the first week by looking at trig relations and using their exponential form. So we have the sum from n equals 1 to infinity of r to the n cosine n x over n. We can write that as 1/2 times the sum of n equals 1 to infinity of r n e to the I n x over n plus 1/2 times the sum of n from n equals 1 to infinity of r times e to the minus I n x over n. All right. Now, the reason why we decided to write it like this is that these are actually useful expansions in their own right. Does anybody recognize what they look like? You might not, and that's okay. What are the kinds of series that we've had to look at before? What are the kinds of expansions that have popped up in this class? Even popped up on the homework.
Natural log of 1 plus x.
Right. So these are actually the expansions, the Maclaurin expansions of log of 1 minus z, where we have z is equal to re to the ix, or re to the minus x. So for example, this term becomes re to the ix plus re to the ix squared over 2 plus re to the ix cubed over 3. And this equals minus the natural logarithm of 1 minus z. And so the punchline for all of this is that we can write this summation from n equals 1 to infinity of r to the n of cosine of nx over n as minus 1/2 times the natural log of 1 minus re to the ix plus the log of 1 minus re to the minus irx. So that's minus the natural log of 1 plus r squared minus 2r cosine x, the 1/2, which you might recognize if you go back to your notes. It might be the second lecture that we did something like this. And what we can finally finish with is for r equal 1 and using Abel's theorem, we can finally write that the sum from n equals 1 to infinity of cosine of n of x, or of nx over n, is equal to minus the natural log of 2 minus 2 cosine of x to the half if we collapse these things, or minus the natural log of 2 sine of x halves if you use a trig expansion or trig identity. Okay. So that's a long way around of saying that this is one use for using the complex Fourier series expansion rather than the sines and cosines. We're kind of running out of time, so I'm going to leave it here. Next time, we're going to look at applications and mostly focus on cosine and sine series. Before I go, anybody have any questions?
Back, I think, like a while ago, actually, when we're going over, I think the square wave, where it was h over 2 plus h over I pi, e to the it plus 1/3, e to the 3it, and then plus 5. Is this supposed to be a 5 or a 1/5?
That's 1/5. Sorry. Thank you.
Okay.
Yeah. Sorry. Good catch. If I find typos in some of this, or wordos, rightos, whatever, I'll mention it online. Okay. I'm sure they're in there somewhere, right? I haven't put the wrong sign bank over here to pull from, just in case. Okay. All right. That's about it. Give yourself a nice little rest. And again, look for an email. I'll send out an email and modify my office hours. I know that trying to have afternoon office hours conflicts with AdLab, and I want to make sure that you guys have a chance to talk to me. Also, because of meetings that I had at the beginning of the term that I don't have anymore, I didn't really have any office hours on Monday, and I realized that the homework is due at the early part of the week, so I want to add in some of those office hours early on, maybe right after class on Monday. Okay? Is that it? Are we good? All right, well, have a great day. I'll see you guys later.
I will.
Thanks a lot.
Thanks, Meg.
Bye, Meg.
Okay.
Bye, Allie.
Bye.